as the voltage source E and have two loops, loop 1 and loop 2, with the Kirchhoff current law. At the node, we have I1 coming in to the node, I3 getting out, I2 getting out. So the relationship of I1, I2, I3 would be the sum that coming in, which is I1, equals the sum of coming out, which is I2 plus I3. And with the Kirchhoff voltage law, for loop 1, the voltage source or the source of voltage E equals as I1 going through the coil or the inductor. So we have L multiplied by the rate of change of I1 with respect to time. As it goes along, the I2 going to the resistor, so plus the R multiplied by I2. This is for the loop 1. And the next for loop 2. For loop 2, the I3 go across the capacitor. So 0 equals the 1 over C times Q3. And the I2 go opposite direction. So going to be negative sign of the R multiplied by I2 as a second equation. And next, again, we're going to write it as the terms or the system of the I1 and I2 equations. From the relationship of the I3 as the rate of change of the charge Q3 with respect to time, we're going to multiply or apply the derivative to the second equation here to be 0 equals 1 over C multiplied by I3 and minus the R times the rate of change of the I2 with respect to T as a second equation. And next, what we have to do is to rearrange the term and substitute with the value. Now the second equation here, after we multiply all by C, we will get 0 equals I3 minus R times C times the rate of change of I2 with respect to T. From the first equation, as E equals 60 volts, and the L equals 1, the R equals 50. The second equation, we still have I3. So we are going to rewrite it as I1 and I2. From the Kirchhoff current law, we can see the I3 as I1 minus I2. So we replace I3 with the I1 minus I2 and replace the R with the value 50 and the C with value 10 to the negative fourth for the C. So now we have the equation. The first one, it looks the same as what provided. The second one, the R times C times the rate of change of the I2 with respect to time plus I2 minus I1, which is the same or the equivalent to the one that we just derived. And with this format of the system of equations, we place the value L as a 1. So we have the di1 dt plus the R, which is 50. So 50 I2 equals the E, which is 60 volts. And the R times C, R is 50 multiplied by 10 to the negative fourth, the rate of change of I2 with respect to time, plus the I2 minus I1 equals 0. And we're going to work on this system of equations. Write it in the systematic way. Introduce the notation for the operator D. So di1 means the rate of change of the I1 or the current I1 with respect to time. Now the first equation becomes di1 plus 50 I2 equals 60. And the second equation, let's simplify the 50 times 10 to the negative fourth. That is 1 over 200. 1 over 200. So we multiply all by 200. the second equation becomes the di2 dt plus 200 I2 minus 200 I1 equals 0, and write it in the notation D form and rearrange it in a systematic way. This one will give us negative 200 I1 plus the D plus 200 of I2 equals 0. And now we are going to eliminate one of the currents, either I1 or I2. Let's eliminate I1. So we are going to multiply the first equation with negative 200 or positive, we can do positive 200, and then apply the operator D to the second equation. So the first equation, which becomes 200 D I1 plus 200 times 50, that is 10,000 of the I2 equals 200 times 60, that is 12,000. Second equation becomes negative 200 d I1 plus d square plus 200 d of I2 equals 0. Add these two equations to eliminate the I1 term. After we add them, we get the d square of I2 plus 200 of the di2 plus 10,000 of I2 equals 12,000. And this is the same as the second derivative of I2 plus 200 times the first derivative of the I2 plus 10,000 of the I2 equals 12,000, or the non-homogeneous linear with the constant coefficient differential equation. And use the auxiliary equation to find the solution of the complementary solution. We have m squared plus 200m plus 10,000 equals 0. Factor completely to get m plus 100 times m plus 100. This case gives us two repeated solutions, which is negative 100 and negative 100. Therefore, this one is a repeated solution. So when we obtain, we're gonna have the first solution as y1 equals e to the not y anymore. So this is the current I2. So I2, the first solution would be e to the negative 100t. The second one is the same pattern, but multiplied by t to make it independent, linearly independent. So now we have I2 complementary solution as C1 e to the negative 100t plus C2 times t e to the negative 100t. And since this is the non-homogeneous, we're gonna find a particular solution for the current I2. And next, we're gonna find the particular solution, which is the I2 subscript P, with the pattern of the function g on the right-hand side. So g of t, or the one that make it non-homogeneous as 12,000, which is a constant term. This is a constant which is not the same as one of the complementary solution. Therefore, the trial solution or the pattern of the particular solution of the I2 would be in the constant term. And that leads to the second derivative, the first derivative, and the second derivative to be 0. And next, we're gonna replace the I2p equals a and its derivatives into the differential equation, which is the I2 double prime plus 200 I2 prime plus 10,000 I2 equals 12,000, sorry. And this is for the particular solution. So add more subscript there. Okay, as a second derivative 0, first derivative 0, and 10,000 multiplied by A equals 12,000. That makes A equals 1.2, which is the complementary part of the solution of the I2. Now we have I2 as a function of the t equals C1 e to the negative 100t plus C2 multiplied by t multiplied by e to the 100t plus 1.2. Okay, and next we're gonna use the I2 to find I1 or the current I1, and using one of the equations provided. So I'm gonna use the second equation, just from the equation in the form of negative 200 I1 plus the derivative of the I2 plus 200 I2 equals 0. Therefore, we get I1 equals the first derivative of the I2 minus 200 of the I2 and then multiply by 1 over 200. That means we're gonna have to find the second derivative or the first derivative of the I2. So I2 prime would be negative 100 C1 e to the negative 100t. Use the product rule for the derivative of the second term to get C2 e to the negative 100t minus 100 C2 times t e to the negative 100t. And then replace it into the equation to find I1. And after substitution, we should get I1 as a function of t in the form of 1/2 C1 e to the negative 100t plus 1 over 200 C2 e to the negative 100t plus 1/2 C2 times t times e to the negative 100t and then plus 1.2 as a general solution for the current I1. Next, we're gonna use the initial conditions. As it said, I1 at 0 equals I2 at 0 equals 0 by substituting into the I1 and I2 to find C1 and C2. So for the I1, which is 0 equals 1/2 times C1 plus 1 over 200 times C2 plus 1.2. And for the I2, we get 0 equals C1 plus 1.2. Therefore, C1 equals negative 1.2. And then we use it to solve for C2. That gives us C2 equals negative 120. After we get the C1 and C2, put them back into the equations for both I1 and I2 to get the solution of this system. As I1 at t equals negative 0.6 e to the negative 0.6, negative 100t, sorry, and minus sign 0.6 c e to the negative 100t, and then minus 60 times t e to the negative 100t plus 1.2. And for the I2, similar way. So I2 at t equals C1, which is negative 1.2 e to the negative 100t plus C2, which is negative 120 multiplied by t e to the negative 100t, and then plus 1.2.